Previously, we implemented a priority queue using heaps. If you don't remember, you should check the video about heaps before continuing, as we are going to be using heaps to sort, which is why this sorting algorithm is called Heapsort. Heapsort is actually quite simple because all the complexity is inside the heap data structure. Here's how to perform Heapsort. Let's say you have an array A to sort. You first initialize your empty min heap H, then all you have to do is insert every element from your array into your heap. Your heap will automatically have the root as the minimum value. All you have to do now is keep extracting the min from your heap and writing it to your array until there are no more elements in your heap. Because of the property of the heap, you're always extracting the minimum every time, so you'll get your elements in ascending order. And because of the structural property, where the binary heap is guaranteed to be balanced, every insert and delete operation is O of log n time. So what is the time complexity for Heapsort? When n is the number of elements in the array, we can think of the time complexity to be this formula. O of whatever it takes to initialize, plus n times the time for insert, plus n times the time for extract min. We initialize the heap, then we have to insert n elements, and then extract min n times. Initialization is O of 1 since we're only creating an empty heap. Insert and delete min are both log of n operations, like we said. Hence we have O of 1 plus n times log of n plus n times log of n, which is equal to O of n log n, since that is the dominant term. The space complexity is O of n since you're creating a separate heap in addition to the array you have to sort. And your heap will contain all n elements when you're done inserting all the elements before popping them off. However, there is a better way to do this because I actually lied about how to perform heap sort. So here is how you actually perform heap sort. Remember that a heap, despite it being a tree structure in concept, in practice, it's actually just an array. So what if we can turn the array we want to sort into a max heap? Why would we want a max heap? Let me show you. Here we have a max heap and the array representation of that heap. Our goal is to sort it. So what should we do? Take the max of your heap, which is the first element of your array, and swap it with the last element of your array. Then, to make sure your heap maintains the heap property, you call fix down on your new root element, which is 6. However, instead of calling fix down on your whole array, you reduce your heap size by 1, excluding the max element you just swapped to the back. So this is your new heap now of size n-1. And the rest of the array will be what will become your sorted array. You do that n times, so you keep swapping the max to the back of your array and then fixing your heap, and eventually your array will be sorted. If we express what we're doing here in code, it would look like this. The heap sort function will take in a, the array to sort, and n, the size of the array. For now, let's just assume that a is already a max heap. While n is larger than 1, we will swap the first and last element, decrease n by 1, and then fix down the root. We will use the expression root and last instead of index 0 and n-1, so it's easier to read the code. If we repeat this until we exit the while loop, we end up with a sorted array. So as you can see, you're going to perform fix down n times. So the time complexity will be O of n log n, like before. But you also save space this time, since you don't require any extra memory. It's an O of 1 space complexity. However, we didn't talk about how we can turn our array into a max heap. There is actually a name for that, for turning an array into a heap. It's called heapify. Heapify takes an array as an input and will turn it into a heap in place, meaning it does not need any extra memory and will perform its operation within the array but swapping around elements. Here's an array we want to heapify and what it looks like if we put it in a heap structure. The key is to call fix down on every single parent. You can actually call fix down on every node in your heap if you want, but it would be redundant to call heapify on leaf nodes since they have no children to fix down to. Hence, for heapify, we first get the array size. That will allow us to get the last element in the heap, which is n minus 1, but we'll just write last of n to make it easier to read. And then you initialize I with the parent of the last node. If you don't remember how to mathematically compute these indices, like parent and last, you should check out the heap video again. All you have to do is loop down to index 0, which will allow you to call fix down on every parent, or aka on every node that has children. Here's an example of calling heapify with the array representation of the heap and the actual heap, so you can see how it works. The time complexity of heapify is O of n. However, we will not do the analysis as it is a little bit complex. Great, so now that we know how to heapify, we can add it to our code for heap sort. So the time complexity for heap sort is O of n log n. Heapify only takes O of n time, but the swapping and fixing down is O of n log n, which is the dominant term. And like we said before, the space complexity now is O of 1. Okay, so that's it for Heapsort. Here's a quick visualization of the whole process with the array and the heap representation of the array. Alright, so that's it for Heapsort, and I'll see you in the next one.